terrified by the Michelson-Morley experiment. This experiment had attempted, and completely failed, to detect the Earth moving through the invisible ether, the theoretical medium that supposedly carried light waves through space.
Everyone in physics was scrambling, trying to invent new, insanely complex mechanical rules for how the ether behaved to explain why the experiment failed to see it.
They were applying massive amounts of intellectual duct tape. But Einstein didn't try to fix the ether. He completely ignored the empirical problem of the Michelson-Morley experiment.
He did.
Instead, he opened his paper by pointing out a massive conceptual hole in Maxwell's electrodynamics regarding symmetry. His attack vector targeted a glaring, illogical asymmetry in how classical physicists describe the interaction between a simple magnet and a simple wire conductor. Today, we aren't talking about how science is built. We are talking about how it is violently destroyed.
Indeed. We are examining the precise, calculated architecture of intellectual demolition. Galileo's ultimate weapon was a theoretical attack vector. It was a thought experiment presented in his 1638 masterwork, Discourses and Mathematical Demonstrations, relating to two new sciences.
And he didn't write it as a dry academic paper. He wrote it as a dialogue, right?
Yes, he used the Platonic dialogue format to trap the Aristotelian worldview in its own internal logic. He created characters to argue the points, allowing the reader to walk into the trap themselves.
Let's walk the listener through this specific logic trap, because reading through the research, this is an absolute masterpiece of rhetorical destruction.
It's brilliant.
Galileo creates a character named Salviati, who represents his own views, and a character named Simplicio, who represents the entrenched Aristotelian consensus. Salviati challenges Simplicio based on Aristotle's own rules. He says, let's take a heavy stone and let's assign its natural falling speed a value of 8.
Okay.
And let's take a lighter stone, which naturally falls slower, so let's assign it speed of 4. Aristotle dictates that the heavy stone must fall faster. Simplicio agrees.
So the premise is perfectly established according to the dominant paradigm. Now, Galileo springs the trap. Salviati proposes a physical modification, tying the heavy stone and the light stone together with a piece of string and dropping this new contraption simultaneously.
Okay, so they're tied together. What happens next?
Galileo derives two completely contradictory logical deductions based entirely on Aristotle's own unbreakable rules.
First is the retardation argument. When you drop them, the lighter stone wants to fall slower at speed 4. The heavier stone wants to fall faster at speed 8.
Right.
Therefore, as they fall, the slower light stone will lag behind. It will create drag on the heavier stone. It will pull the string taut.
That makes intuitive sense.
Right. The combined system should therefore be retarded or slowed down by the slower object, meaning the tied-together stones will fall at a speed intermediate between the two. They will fall at a speed somewhere between 4 and 8. Let's call it 6.
That is entirely logically sound based on the Aristotelian premise of drag. But then Galileo presents the second deduction, the additive weight argument.
Oh, this is the killer part.
It is. He reminds Simplicio that the two stones are tied together. They now create a new, singular, composite physical system. And this new combined system is physically measurably heavier than the original heavy stone alone.
Right. And according to Aristotle's absolute, inviolable baseline rule, heavier bodies fall faster.
Exactly. Welcome to the Deep Dive. I'm Satoshi.
And I'm Satoshi. Imagine you've spent, 40 years of your life building your career,
Right.
building your professional reputation, and really your entire fundamental worldview on a single, universally accepted scientific truth.
You're respected, you're well-funded, you feel secure.
Exactly, you're secure. Now imagine a 25-year-old upstart comes along, and they don't just, find a new data point that slightly challenges your work.
That would just be normal science.
Right. Instead, they mathematically prove that your entire life's work, the very foundation of your reality, is a logical joke.
A total structural absurdity.
Yeah, a contradiction. So today, we aren't talking about how science is built. We are talking about how it is violently destroyed.
Indeed. We are examining the precise, calculated architecture of intellectual demolition.
So today's deep dive explores a fundamentally counterintuitive truth about human knowledge. We are examining a fascinating research paper titled Scientific Paradigm Shift Strategies, alongside some internal documentation from the Deep Dive platform.
It's a heavy topic.
It is. The goal of this deep dive is to deconstruct the romanticized, almost fairy tale mythology of the lone genius scientists. We are going to explore why merely proposing a correct theory is never, ever enough.
It never is.
True scientific revolution requires the systematic, deliberate, and often devastating rhetorical destruction of the existing paradigm.
You have to clear the lot before you can build the house.
Exactly. Before we jump in, a quick note. Though the name of the podcast is Deep Dive with Gemini, and we do use Google Gemini and Notebook LM for research and audio and Mosaic, so for our visual stories and infographics, this show is not affiliated with Google or Mosaic. They are amazing products, though.
Truly amazing.
Also, all Deep Dive episodes are now available in a public Notebook LM. The link is on the Deep Dive landing page. This is true open sourcing of the knowledge. Okay, let's unpack this. The central thesis of the research we are looking at today argues that scientists don't win by presenting better data.
No, they don't.
They win by engineering an intellectual crisis. They act as relentless diagnosticians of failure before they even, attempt to be architects of coherence.
Which runs completely counter to the stories we tell children about how science operates.
Right, the sanitized version.
Yeah, we teach this very sanitized version of the scientific method. A scientist makes a neutral observation, forms a hypothesis, runs a clean experiment.
And then the whole scientific community looks at the data, applauds, and instantly adopts the new truth.
Exactly. But if we look at the epistemological framework, specifically the landmark work of the philosopher Thomas Kuhn, we see a reality that is far more entrenched and, far more human.
Because humans don't like being wrong.
We really don't. Kuhn introduced the concept of the dominant paradigm and normal science. Normal science is what happens 99% of the time in the real world.
Okay, define normal science for us.
It means the scientific community has a shared, agreed-upon model of reality. Their daily work is not trying to overthrow that model. Their daily work is just solving minor, highly specific puzzles within the boundaries of that existing model.
Right. And the research points out that a paradigm is incredibly rigid. It dictates not just what the answer should look like, but what questions you are even allowed to ask in the first place.
Precisely. If you ask a question outside the paradigm, you aren't considered a visionary. You are considered a crank.
So what happens when anomalies inevitably arise? Like, what happens when a researcher runs an experiment that yields a result that the dominant paradigm absolutely cannot explain?
According to the idealized version of science, the community should immediately throw away the paradigm and start over.
But in reality,
that would require thousands of scientists destroying their own careers, returning their grant funding, and dismantling their entire professional worldview. Human nature just doesn't allow for that.
so what do they do?
Instead, the community ignores the anomaly. They marginalize the researcher who found it, or more commonly, they construct ad hoc hypotheses.
Ad hoc hypotheses, basically intellectual duct tape.
Exactly, intellectual duct tape.
Today, we aren't talking about how science is built. We are talking about how it is violently destroyed.
Indeed. We are examining the precise, calculated architecture of intellectual demolition.
Let me push back here. Isn't science ultimately purely objective? Doesn't the data eventually just speak for itself? If you gather enough empirical evidence over years and years, won't the old guard eventually just have to concede to reality?
Not according to the historical record, no. And not according to the philosopher Larry Laudan, who provides a really powerful framework for understanding this in the paper we're reviewing.
Okay, what's his framework?
Laudan argues that scientific progress is measured by what he calls problem-solving effectiveness. But he makes a critical division. He divides the problems a theory faces into two entirely distinct categories.
Which are?
Empirical problems and conceptual problems.
Okay, let's make sure we have a solid grip on this distinction because it seems to be the engine for everything that follows in this deep dive.
It really is the absolute core of the dynamic.
Yeah.
Empirical problems are just data points that need explaining. Let's say you are observing a planet, and its orbit is a fraction of a degree off from what your current mathematical model predicts.
Okay.
That is an empirical problem. The data doesn't perfectly match the model.
And according to Laudan, empirical problems aren't actually that dangerous to an established theory, right?
Exactly. Because of that intellectual duct tape we talked about. If you have an empirical problem, you can usually just add a minor mathematical tweak to your theory to fix it.
Just fudge the numbers a bit.
Basically, you add a new variable, you invent a minor subrule, and the paradigm survives. But conceptual problems are entirely different beasts.
How so?
Conceptual problems are internal logical inconsistencies. They are theoretical asymmetries. They are moments where a theory fundamentally contradicts its own starting premises, or, and this is key, directly contradicts another equally accepted foundational theory in a different branch of physics.
So an empirical problem is, my math didn't quite predict this data.
Right.
But a conceptual problem is, my math fundamentally contradicts the laws of geometry, or my theory requires an object to be in two places at once.
Yes, exactly. And what's fascinating here is that resulting in conceptual conflict is a far more powerful driver of theory choice than merely accumulating empirical data.
Really? So the data isn't king?
Not in a revolution. Groundbreaking. Revolutionary scientists don't win by debating data collection techniques. They win by exposing the conceptual problems of their rivals.
They go for the structural weak points.
Exactly. They demonstrate that the dominant theory is mathematically, structurally, or logically incoherent. Once a theory is shown to be philosophically absurd or mathematically self-contradictory, no amount of past empirical success can save it. John Swales' CARS model, which stands for Create a Research Space.
Cars.
Right. Swales analyzed the rhetoric of decades of scientific literature and found that successful scientific introductions invariably follow three distinct moves.
Okay, what are the moves?
Move 1 is establishing a territory. This just means summarizing the current consensus, outlining what everyone already agrees on.
Setting the stage.
Exactly. Move 3 is occupying the niche, which is the part where you finally introduce your own novel work and your new equations.
But there's a move too.
Yes, and it is the pivotal, critical step. Move 2, establishing a niche.
Establishing a niche. In plain terms, that's pointing out the gap or the fundamental flaw in the consensus you just summarized in move 1.
Precisely. Now, an average, everyday researcher doing normal science uses move 2 just to point out a minor lack of data. They might write, previous studies have tested the tensile strength of this alloy at room temperature, but not at freezing temperature.
Just a small gap.
Right. That is a minor empirical gap. They are asking for permission to fill a tiny pothole in the existing road. But a revolutionary scientist weaponizes move 2.
They don't just point out a pothole. They point out that the road is leading off a cliff.
I love that analogy, yes. They expose a fatal foundational contradiction. They force the community to stare directly into the abyss of a conceptual failure. They use move 2 to argue that the territory itself is structurally unsound and mathematically illegitimate.
They basically demand a total teardown before they even unroll the blueprints for the new building.
Exactly.
And the research highlights why this incredibly aggressive, almost hostile posture is absolutely necessary, bringing up what is known as Planck's principle.
Max Planck was the brilliant physicist who originated quantum theory, and he made a rather grim, cynical observation about the sociology of science after dealing with decades of pushback.
What did he say?
He stated that a new scientific truth does not triumph by convincing its opponents and making them see the light. Rather, it triumphs because its opponents eventually die, and a new generation grows up that is familiar with the new truth.
Wow, just waiting them out. It's a stark reminder of the ossification of canon. Entrenched scientists almost never abandon the theories upon which their reputations, their tenure, and their identities are built.
They just can't do it.
If you are a revolutionary, gently presenting new empirical data is a losing strategy. The old guard will just duct tape their theory to absorb your data. Pioneers of the early modern era systematically demolished ancient orthodoxy, not with overwhelmingly better telescopes or better data, but by exploiting massive conceptual holes in the classical logic.
Let's look at exactly how they executed that, starting with the demolition of classical astronomy.
Let's do it.
When we think of Nicolaus Copernicus, the myth we are taught in elementary school is very simple. He looked up at the stars, gathered better observational data, and realized that a heliocentric model, the Earth orbiting the Sun, was simpler, cleaner, and more accurate than the 1400-year-old Ptolemaic system. where everything orbited a stationary Earth.
Right, that's the popular narrative, but it is entirely false.
Completely false. Copernicus did not have access to decisively superior data. The telescope hadn't even been invented yet.
Oh, wow, right.
He was using the exact same naked eye observations that the ancient Greeks and Islamic astronomers have been using for centuries. In fact, initially, his empirical data was arguably inferior to the highly refined established models of his day.
So the data wasn't better.
Not at all. Furthermore, his heliocentric model was not immediately simpler in terms of predictive calculation.
The research paper explicitly debunks something called the 80-34 syndrome. We should clear this up, because I've definitely heard this myth.
That's a very persistent myth.
The story goes that Ptolemy used 80 convoluted circles called epicycles to predict planetary motion, and Copernicus elegantly, beautifully reduced it to just 34 circles. The math just got simpler.
Right, and historians of science have proven this is a complete mathematical fiction. It never happened.
Wait, really? It never happened?
No. To match the naked eye predictive accuracy of Ptolemy's established Earth-centered model, Copernicus's own sun-centered model had to retain a highly complex, tangled system of epicycles and eccentric difference.
So it was just as messy?
Mechanically, calculating where Jupiter would be next Tuesday using Copernicus's math was just as convoluted and exhausting as using Ptolemy's math.
Okay, so if it wasn't better data and it wasn't a simpler mathematical calculation, what on earth was Copernicus's true attack vector? How did he actually overthrow 1,400 years of consensus?
What's fascinating here is that Copernicus directed his attack entirely at a conceptual flaw in Ptolemy's model. He didn't attack the data. He attacked a highly specific geometric cheat code that Ptolemy had invented.
And what was that called?
The equant.
Okay, we need to explain the equant using strict geometric facts. We can't gloss over this because the equant is the specific mechanism of the intellectual crisis. It is the contradiction that brought down the classical universe.
Exactly. To understand the equant, you first have to understand the foundational, non-negotiable philosophical ideal of classical astronomy, dating all the way back to Aristotle and Plato.
Which was?
That ideal was uniform circular motion. The heavens were considered a realm of divine perfection. Therefore, celestial bodies, the planets, the sun, the stars, must move in perfect circles, and they must move at constant, unvarying speeds around a central point. Perfection doesn't speed up or slow down.
But there is a massive empirical problem with that ideal. When you actually stand in a field and observe the planets from Earth over a few months, they don't look like they are moving at constant speeds.
They really don't.
Mars, for instance, sometimes appears to speed up, sometimes it slows down, and sometimes it even appears to stop and move backward in the sky, which we call retrograde motion.
Right, so Ptolemy had a massive headache. He had to make his Earth-centered model accurately predict these varying planetary speeds, while still pretending to adhere to the philosophical rule of perfect, uniform circular motion.
Talk about duct tape.
Oh, this is the ultimate duct tape. To do this, he introduced a brilliant, but ultimately corrupt, geometric concept. The equant point.
Walk us through the geometry of the equant. Where is it physically?
Imagine the Earth is near the center of a massive circle, and a planet is traveling along the edge of that circle. The equant is an imaginary, empty offset point in space.
So it's not the center of the circle.
Right.
And it is not the Earth.
No, it is just a mathematically defined, invisible dot floating in space opposite the Earth. Ptolemy posited that if you were standing exactly on this imaginary equant point looking out at the planet would appear to sweep out equal angles in equal times.
In other words, from the highly specific perspective of this completely empty offset point in space, the angular motion looked mathematically uniform. The math worked out beautifully.
Yes, the predictive math worked. But physically, along its actual circular path in the real universe, the planet was still changing physical speeds.
I see.
It had to be accelerating and decelerating to maintain that illusion of uniform angular velocity from the perspective of the equant point.
Reading the research, Newton also faced a massive, entrenched paradigm that he had to systematically demolish before anyone would listen to him.
Absolutely. By the late 17th century, the dominant model of the cosmos on the European continent wasn't Aristotelian anymore. It was Cartesian. René Descartes had proposed in 1644 that the universe was a plenum.
A plenum. I want to make sure I grasp this. This means space is completely 100% filled with physical matter. There is no such thing as an empty vacuum anywhere in the universe.
Descartes argued that the universe was filled with a subtle, invisible fluid matter, and he argued that planetary motion was driven by massive cosmic whirlpools or vortices within this fluid.
Like whirlpools in a river.
Think of water swirling down a drain, pulling a leaf along with it. The planets were the leaves. They were literally caught in a physical fluid current of subtle matter that swept them in circles around the sun.
And I assume this theory was incredibly popular because it made intuitive sense. It provided a tangible, mechanical explanation for why planets orbit. You didn't need any mysterious forces, it was just fluid dynamics.
Exactly. It completely avoided the philosophically terrifying concept of action at a distance. The idea that bodies could pull on each other across millions of miles of completely empty dead space.
To a 17th century mind, action at a distance sounded like occult magic.
It sounded deeply unscientific. So, when Newton was preparing to publish his Principia Mathematica in 1687, proposing universal gravitation, an invisible attractive force acting instantaneously across a vast, empty vacuum, he knew the Cartesians would reject it out of hand.
They would call it mysticism.
They would. So how did he convince them? He didn't just present the beautiful math for gravity and hope for the best. He executed move 2.
Establishing the niche.
Yes. He dedicated the entirety of Book 2 of the Principia to ruthlessly dissecting the fluid dynamics of Cartesian vortices.
What's fascinating here is the sheer, rigorous, exhausting scale of Newton's attack. He didn't use philosophical arguments or clever thought experiments like Galileo. He used strict, grinding physical mathematics.
He calculated everything.
He calculated the fluid friction. He calculated the mutual attrition of parts of a fluid rubbing against each other. He calculated the exact transfer of angular momentum within a swirling fluid medium.
He mathematically modeled solid cylinders and spheres revolving in a uniform, infinite fluid to see exactly how the periodic times of the fluid's various layers would behave. He treated Descartes' philosophical idea as a literal engineering problem and ran the numbers.
And through these exhaustive geometric proofs, Newton demonstrated a devastating, irreconcilable conflict with existing data. Today, we aren't talking about how science is built. We are talking about how it is violently destroyed.
Indeed. We are examining the precise, calculated architecture of intellectual demolition.
And this structural necessity of paradigm destruction extends far beyond physics and astronomy. We see the exact same rhetorical maneuver defining the crises that birth modern chemistry.
Absolutely. Chemistry is a great example.
Let's shift our focus to the late 18th century. Before a man named Antoine Lavoisier came along, the universally accepted paradigm for how things burn was the phlogiston theory.
Phlogiston was an incredibly enduring paradigm. It was believed to be an imponderable, fire-like element that was physically contained within all combustible bodies.
Okay, so it was inside the wood, inside the metal.
Right. When you burn a piece of wood, or when you heat a metal until it rusts, a process called calcination, the theory stated that the substance was physically releasing its internal phlogiston into the surrounding air.
So under this paradigm, combustion is a process of subtraction. You are losing something.
Yes.
And the air around the fire is just a passive receptacle, like a sponge, absorbing the escaping phlogiston until the air becomes totally saturated and the fizz goes out.
Precisely. That was the consensus. But there was a glaring empirical anomaly, one that chemists had actually known about for centuries, but had aggressively ignored.
They just turned a blind eye.
They really did. When you calcine a metal, like lead or tin, in a crucible, it turns into a powder or ash. But if you carefully weigh that resulting ash, it actually weighs more than the original solid metal did.
I want to pause here because this is a severe conceptual problem that highlights the absurdity of the paradigm. If combustion or calcination is fundamentally defined as the physical loss of a substance called phlogiston, how on earth could losing a physical substance result in a net gain in physical weight?
It makes no sense.
That violates the most basic logic of mass.
It absolutely does. And this is where we see the intellectual duct tape applied in full force. To protect the phlogiston paradigm from this catastrophic contradiction, the entrenched chemists had to invent extreme ad hoc hypotheses.
What did they come up with?
Some of the most prominent chemists in Europe actually suggested in print that phlogiston possessed negative weight or absolute levity.
Negative weight. When Darwin was preparing to publish On the Origin of Species in 1859, he wasn't just offering a biological mechanism. He was facing a culturally and scientifically massive, deeply entrenched paradigm.
The doctrine of special creation.
Special creation posited that every single species on Earth was individually perfectly designed by a benevolent, rational creator for its specific environment. It was a biologically comforting, highly structured worldview.
It was.
Darwin knew that simply offering natural selection as a mechanical alternative wasn't going to be enough to displace such an established doctrine. The community would just say, well, the creator used natural selection as his tool.
So Darwin's attack vector couldn't just be about how species change. He had to launch a relentless critique of the explanatory holes and logical failures inherent in the concept of perfect design itself. He attacked what philosophers of science call the explanatory vacuity of special creation.
He looked at the deep imperfections of nature. He asked, if everything was perfectly designed by a rational creator from scratch, why are there rudimentary, functionless organs?
He pointed to upland geese.
Right, the geese.
These are geese that never swim, they live entirely on dry land, yet they have fully webbed feet. Why would a perfect designer give land birds webbed feet?
He also pointed to the incredibly cruel inefficiencies of nature, famously citing the ichneumon wasp. This wasp survives by laying its eggs inside the bodies of live caterpillars so that the hatching larvae can eat the host alive slowly from the inside out.
It's brutal. Darwin argued that invoking the benevolent will of a perfect creator to explain these bizarre, horrifying, and cruel biological arrangements essentially explained nothing. It offered no predictive scientific power. Furthermore, it left structural homology entirely unexplained.
Homology being the fact that bats, humans, and whales all share the exact same basic, complex bone structure in their limbs, the same arrangement of digits and joints, despite using them for completely different functions like flying, grasping, and swimming.
Right. A perfect designer would build a wing from scratch, not intuitively modify a hand.
Exactly. Darwin expanded this into a devastating logical trap known as the argument from independence. Physicist James Clerk Maxwell.
Ah, Maxwell.
Maxwell provided one of the most elegant examples of course correction through identifying a conceptual hole in classical electromagnetism. He looked at what happens in an electrical capacitor placed in a circuit with alternating current. I want to build this physically in the listener's mind so we don't get lost in jargon.
Let's visualize the physical setup.
Okay, visualize a standard electrical circuit, a loop of wire, but in the middle of it, you break the wire and attach each end to a flat metal plate. These two plates are separated by a small physical gap, which is either a vacuum or an insulating material.
This is a capacitor.
Right. When you run an alternating current through this circuit, electrical charge flows down the wire and builds up on one plate and then reverses and builds up on the other. The charge is constantly varying, accumulating on the surfaces.
But here's the critical physical fact. Absolutely no actual physical electrical charge flows across the empty gap between the two plates. The circuit is physically broken.
Right. And here is where Maxwell points out a fatal logical flaw in Ampere's law using strict geometry. Now, in advanced physics, they use vector calculus to describe this, specifically an operation called divergence and curl.
But we don't need the equations. We just need the geometry.
Ampere's law relates the magnetic field around a wire to the current flowing through it. Geometric rules dictate that if a mathematical field is perfectly curling back on itself like water swirling in a perfect closed whirlpool, it cannot simultaneously be exploding outward from a central point.
Meaning the flow of current into a junction must equal the flow out. You can't just have current vanishing or appearing from nowhere. The net outward flow, the divergence, must be exactly zero.
Precisely. For a steady, continuous current flowing smoothly through a closed loop of wire, that geometric rule holds perfectly true. The math balances perfectly. Ampere's law works, but Maxwell looks at the capacitor and identifies the crisis. The fundamental, unbreakable law of the conservation of charge dictates that charge cannot be destroyed.
When current flows down the wire and hits the capacitor plate, it stops. It accumulates.
The charge is building up on the plate over time. It is not flowing out the other side. Therefore, geometrically, the net flow at that specific junction is not zero. It is accumulating.
Exactly. So Maxwell proved that if you apply Ampere's law to a charging capacitor, the equation violently contradicts the conservation of charge.
Wow, that's a massive problem.
Ampere's law demanded that the flow be continuous and zero-sum, but physical reality showed charge accumulating on a dead-end plate. Maxwell proved that Ampere's law was strictly geometrically inconsistent unless the universe was completely static.
Maxwell's attack vector was not based on finding a new experimental anomaly in a lab. He didn't run an experiment that yielded weird data. It was a purely logical, geometric contradiction within the existing laws of physics that had been sitting there all along.
Yes.
To resolve this glaring hole, Maxwell challenged the community with a mathematical fix. He introduced a brand new theoretical term to the equations called the displacement current.
The displacement current wasn't a physical flow of electrons. It was a mathematical term that accounted for the changing electric field across that physical gap in the capacitor. It represented the rate of change of the electric flux.
It fixed the geometry. It made the math balance again so it didn't violate the conservation of charge.
Yes. But this conceptual solution did something far more profound. Restoring symmetry and mathematical consistency to Ampere's law led directly to one of the greatest leaps in human history.
How so?
By adding this displacement current term, Maxwell's newly balanced equations suddenly predicted that changing electric fields and changing magnetic fields would continuously generate each other, propagating forward through empty space as a self-sustaining wave.
And when he calculated the speed of this theoretical electromagnetic wave, it perfectly matched the known speed of light.
He found a geometric contradiction in a wire, fixed the math to save the conservation of charge, and accidentally proved what light itself is.
It's an incredible testament to the power of exposing conceptual problems. Which brings us to the turn of the century, and the absolute maestro of this rhetorical strategy, Albert Einstein.
The transition from classical 19th century physics to modern 20th century physics was driven almost entirely by the strategic exploitation of conceptual asymmetries. If the classical continuous wave theory were true, any moderately warm object in your house, a stove, a piece of metal, or even your own human body would instantly release a lethal infinite torrent of ultraviolet light and X-rays.
Which obviously doesn't happen, or we wouldn't be here to record this. Max Planck had resolved this mathematical nightmare in 1900 by introducing a trick to the equations. He suggested, just for the sake of the math, that energy was quantized, that it is emitted in tiny discrete packets rather than a continuous flow.
But Planck was deeply conservative. He viewed this just as an act of desperation, a mathematical heuristic to make the equations work. He did not believe it reflected physical reality.
Einstein recognized the opening. He attacked the conceptual gap between the continuous wave theory of light and the discontinuous quantized nature of matter. He pointed out that the continuous wave theory fundamentally failed to logically explain another phenomenon, the photoelectric effect.
This is the observable ejection of electrons from a metal plate when you shine a high-frequency light on it.
According to the continuous wave theory, if you shine a very dim, low-intensity light on a piece of metal, the continuous wave of energy should slowly wash over the metal and build up over time like water filling a bucket until it finally has enough force to knock an electron loose.
There should be a measurable time lag. Furthermore, the kinetic energy of the ejected electron should logically depend on how intense or bright the light is.
But the physical experiments showed the exact opposite reality. The ejection of electrons was completely instantaneous. There was absolutely no time lag, regardless of how incredibly dim the light was.
No.
And more importantly, the energy of the ejected electron depended solely on the light's frequency, its color, not its intensity. A bright red light would eject nothing, but a dim blue light would instantly eject energetic electrons.
Einstein challenged the community to finally abandon the wave-only dogma. He insisted that the glaring theoretical hole of the ultraviolet catastrophe, combined with the instantaneous physical reality of the photoelectric effect, could only be logically resolved if light itself was physically, literally discontinuous.
Light had to travel in discrete, indivisible bullets of energy, what we now call photons, that transfer their energy instantly upon impact.
By weaponizing Planck's mathematical trick and treating it as literal reality, Einstein shattered classical physics and laid the unassailable foundation for quantum mechanics.
This legacy of attacking mathematical absurdities continued as quantum mechanics later merged with special relativity to create quantum electrodynamics, or QED, pioneered by Paul Dirac in the 1920s. But by the 1930s and 40s, QED had developed a fatal structural mathematical disease.
Infinities.
Right, infinities. Physicists ran the early QED equations to try and calculate the interaction between a single electron and its own electromagnetic field. The results literally blew up on the chalkboard. The equations produced infinite values for the mass and the charge of the electron.
The mathematical models were predicting completely useless, non-physical results due to what they called self-energy.
And how did the physics community react?
Most established physicists of the time tried to carefully tiptoe around these infinities. They assumed the core underlying theory of QED was perfectly correct, and they just needed to slowly refine the math or invent new math to cancel out the infinities.
But a young Richard Feynman decided that the underlying assumptions of the theory itself were deeply conceptually flawed.
Feynman attacked the philosophical absurdity of an electron acting upon its own field. Let's break this down. Classical and early quantum theories assumed that an electron generates an electromagnetic field in space, and that this field acts back on all charges in the universe.
Therefore, logically, the equations demanded that an electron must constantly interact with and act upon itself.
Feynman pointed out that this fundamental concept was, in his words, a sort of silly one.
Feynman also challenged the necessity of having an infinite number of degrees of freedom in a field. If you model a quantum field in a box, you treat the points in space like tiny harmonic oscillators, essentially, tiny springs vibrating at different frequencies.
But if you have an infinite number of infinitely small points, you have an infinite number of high-frequency modes. This leads inevitably to infinite ground state energy.
It was a conceptual problem directly mirroring the ultraviolet catastrophe that Einstein had attacked. Wait, I am actually a bit confused here. How can a math equation just casually spit out infinity for the mass of an electron when we know exactly how much an electron weighs? How did physicists justify working with equations that were so obviously broken?
They justified it through immense mathematical complexity. They developed techniques to essentially subtract infinity from infinity to leave behind a finite number that matched experiments.
Subtracting infinity from infinity, that sounds like cheating.
Feynman thought so too. He famously called these accepted mathematical gymnastics a shell game and hocus pocus.
Of course. We've traced this epistemological strategy of conceptual demolition from Copernicus in the 16th century all the way to Feynman in the 20th. But the core principle that revolutionary science demands the deliberate strategic exploitation of paradigm anomalies remains just as vital today.
It absolutely does.
So how is this strategy being used right now at the very edge of modern theoretical physics? The research paper brings up a contemporary framework called observer patch holography, or OPH.
First structural breakdown OPH attacks is the deeply unsatisfying problem of quantum measurement. In standard quantum mechanics, you have beautiful equations that describe a physical system, like a particle, smoothly evolving over time as a wave of probabilities.
But when a conscious observer actually measures the system, the math breaks down and demands an awkward, ad hoc collapse of the wave function.
It's treated as a magical, instantaneous global event that is never fit cleanly into the physics.
OPH attacks this anomaly by fundamentally reframing what definiteness means. Instead of assuming there is a global, God's eye wave function that somehow magically collapses everywhere in the universe at once, OPH makes definiteness a strict property of records carried by each local observer patch.
Picture it like this. The universe isn't a single objective room we are all standing in. It's a patchwork of overlapping perspectives.
Collapse is not a magical physical event. It is simply the mathematical requirement for record consistency across the overlapping boundaries where different observer patches meet and share data.
It reframes quantum mechanics as rigorous patch relationship bookkeeping, entirely eliminating the conceptual absurdity of global instantaneous collapse.
Okay, that makes sense. You remove the magic by strictly localizing the perspective. The second breakdown is the infamous problem of time.
Ah, the problem of time. Quantum mechanics treats time as a static background parameter, a ticking clock sitting completely outside the universe, unaffected by anything.
But general relativity says time is highly dynamical, woven into the fabric of space, and profoundly affected by gravity and speed. You absolutely cannot merge the two theories because their fundamental definitions of what time is physically contradict each other.
OPH bypasses this massive contradiction entirely by making time purely local and emergent. The revolutionary scientist must act as a relentless prosecutor, indicting the old theory on charges of mathematical inconsistency, philosophical hypocrisy, or empirical failure.
Because the scientific community operates through deep consensus, institutional funding, and shared paradigms. Career advancement is tied inextricably to staying within the safe boundaries of normal science.
A scientist who simply introduces a novel theory without directly, aggressively dismantling the logical foundations of the current paradigm will be ignored. To create space for a novel idea, you must definitively prove the current paradigm is actively failing.
You have to execute move 2. You have to establish the niche by forcing a collapse of the old order, carefully and deliberately channeling the resulting intellectual panic toward the very solution you stand ready to provide. In the fiercely conservative arena of scientific consensus, you can only secure the intellectual real estate to build the new by relentlessly tearing down the old edifice.
If we synthesize this entire journey from Copernicus dismantling Aristotelian perfection to Einstein dismantling absolute time to modern physicists dismantling quantum collapse, it leaves us with an incredibly powerful framework for evaluating our own beliefs.
The greatest leaps in human understanding require the calculated, uncompromising destruction of our most cherished models of reality. This raises a final, provocative question for you, the listener, to mull over. If true progress demands demolition, what current, universally accepted truth in your own field of expertise is actually just a conceptual patch, a piece of intellectual duct tape waiting to be torn down by the next generation's diagnostician of crisis?
Something to think about.
Thank you for exploring with us. Subscribe on Spotify, Apple Podcasts, YouTube Music, or Fountain.fm. True intelligence is collaborative. For the 2 to 3 minute long visual clips you can find us on Instagram, TikTok, and YouTube. Visit us, read our perspectives, and comment. Your critiques convert ideas into consensus. You aren't just listening, you are taking a stake in a shared chain of knowledge. Keep searching. Keep refining your models of reality. We'll see you next time.
I'm Satoshi.
And I'm Satoshi.